Hello everyone, this is Amir from Audio Science Review. I've had a few requests in the past to cover less traditional approaches to building DACs, digital to analog converters. And I recently reviewed a product of that type. It's from a company called Audio-gd in China. The specific model that I tested is called the Master 7 Singularity. You can see the title over here, pretty fancy sounding name. I've tested a number of products from this company before when I first started measuring electronic equipment, and the performance was quite poor. And the other thing was weird is that the company shows measurements on their site, and my measurements never matched theirs. And, it turns out that just their measurements are just obscure, even though their outputs are audio precision, there are no scales on them or test conditions. And at any rate, it never seemed like what they were showing was accurate. And a lot of people bought their equipment, I think, because they saw the measurements and assumed that products were that good. Fast forward 2 or 3 years later, people were wondering if the products had improved, and a member was kind enough to loan me a much more recent product. This one came out in 2018. It's discontinued again. They seem to have a revolving door as far as DACs and version numbers, but it's a lot more recent than the equipment that I tested in the past. And the owner bought this around, I think it's at spring of 2018, so not that old. On this thing. It's one of the heaviest and largest DACs I've tested. It's a massive box and it's quite deep. I've already shipped it back to the owner, otherwise I would show you. But in this picture, the perspective doesn't show it, but it is very, very deep and very, very wide and very heavy. I think it's like, I don't know, 20 kilograms or, 40, 50 pounds or something like that. And if you go look at the picture down here that I have of it, you'll see why. It's got these 3 giant transformers in the front together with this large chassis. And that makes it quite heavy. When you look inside of it, oh, by the way, the price is pretty high. This is a $2,500 DAC. So compared to a desktop DACs that we measure for a few $100s, it's about 10 times the price. And you do get 10 times the weight and maybe a hell of a lot more than 10 times the components. The heart of this DAC is this TI PCM 1704 Dac chips, and they actually use 4 of them in each channel. You can see a row of them over here and a row of them over here. When you combine DACs, you can improve their signal-noise ratio because the output scales linearly, but the noise doesn't combine linearly, so you gain signal-noise ratio. So quite an attempt in here to try to do this. This Dac chip has been discontinued. So they probably bought all they could, and then when they couldn't buy any more, they stopped building it. I don't know if they still have stock and using other products. And there's quite a bit of fat out there as far as people wanting these more older DAC chips, even though the newer ones easily outperform them. And there's this mystique around them, and the moment the manufacturer says they're using these DACs in non-oversampling, which is one of the modes this supports, many people have warm fuzzies about this. And anyway, that's why this company's chosen to go this route. But typical of their products, they also use a ton of discrete components. You can't see them in the picture, but these are all little transistors. Instead of using a single IC, op-amp that handles amplification and buffering, they built their own circuit, which can perform well if done right. And we'll see later on whether this one does or not. And so this is one channel of the DAC on the right. This is the other channel of the DAC on the right. And then in the middle is all the digital logic and control. There's a FPGA chip over here, Alterate, I think. And that's basically programmable logic. You can use specialized tools where you can design a, complicated logic circuit, and then you embed it and download it into this chip. And it morphs into what that circuit is. So it is able to encapsulate thousands and tens of thousands of, discrete parts, and they're large ones that can hold, millions of such components. I don't think this one's that big. But anyway, they use this thing for clocking functions. You have multiple inputs, they all have different formats, and you got to get everything in a way that these standalone DAC chips can accept. So that's all in here. What makes it large and complicated also is that they have these 3 transformers, then they have these very elaborate 3 power supplies over here. Also one for left channel, one for right channel, one for this digital section. So as far as paper goes and paper design goes, this seems like very, very overdone and on a good side. If you're gonna throw kitchen sink at the design, as long as you do it right, should incrementally improve things and certainly shouldn't hurt things. And anyone looking at the picture of this thing will say, wow, this is a hell of a lot more impressive than getting a desktop DAC that I test. That, if you take the top off, is very, disappointing. There's only a few ICs, hooked up together, and the whole board maybe, fraction of the size of this. So ostensibly, it feels good. It even feels good to me as an engineer. I look at this, they're like, wow, a lot of design work went in there. One disappointing thing is that they always provide the USB as a USB input as an add-on card. I could understand 10 or 15 years ago doing that, but it's sitting over here bolted on sideways in here and connected in the back, and you have to pay extra for that. And I don't know if that's still the case, but a lot of times you paid another $150, $200 just to have USB. And USB is the most common input to these DACs today, so it shouldn't be an afterthought, it should be a standard part. I got a kick out of, if you go through the manual, there's no manual, it's just a little 1 page on their website, there's the manual. And it starts right away with this red note over here that they actually have burned in this device for 300 hours before they shipped it to you. Credit to them, instead of saying you have to listen to it for 300 hours. But they go back and say other people have said you got to burn it for another 150 hours and maybe even more, and up to 1,000 hours may be beneficial. I don't know about you, but I'll be old and dead waiting for 1,000 hours just to use this $2,500 DAC. But anyway, they say another 700 hours of burning may be used. So thankfully, this came from an owner who's used it for 3 or 4 years, so maybe it is already at 1,000 hours. I don't know. There's no hour meter on it. If they want to insist on these things, then they better have an hour meter, just like a lot of generators and what have you have it. Suggestion for them in the future: put an hour meter, so you know if it's been burned in. When I started to measure this DAC, I usually, start with this dashboard. Those of you who have seen my reviews, will remember this. But as I ran this, every 2 to 3 seconds, or it seemed to be, all the numbers would randomize, and the generator would have, the analyzer would have to relock to the signal. And I noticed that this frequency measurement, which right now says 1 kilohertz right on the money, would jump down to a 0.999 number, and then immediately switch back to this 1 kilohertz. And I was like, whoa, what the heck is going on there? Let's see if I can trace that. So I ran the same 1 kilohertz tone, but this time I asked the analyzer, as time went by, to just plot the frequency counter. And so it plots it at 1 kilohertz right on the money. Boom, 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 it's gone. And all of a sudden, at 1.5 seconds, we get a sudden drop in clock to this precise number of 0.9930 kilohertz. And then it goes back up to 1 kilohertz and continues, and then it glitches down, then it goes and glitches down, and this continues forever. This is a fatal design error. Basically, they're trying to synchronize on some internal DAC clock to another device that's generating data. So in this case, let's say the clock on a DAC and the clock on a USB module. And you can get into situations where they lose lock, or a buffer overruns or underruns. That means that they're not able to regulate the speed of the two interfaces together so that they stay in sync. And right there, a glitch happens. Now, glitch is very short. I don't know how audible it is, but it's certainly very measurable, and it's just a sin. I mean, the whole purpose of having that FPGA and elaborate clocking and everything that it does is to not have this. And the fact that it winds up with a clear signaling error and design error is just boggles my mind, especially in something that's high-end. I don't know how they don't see something as simple like as this. This is a verification that you do in your design, and it's extremely rare to find this, and here it is happening. And what I had to do then to capture the graph is that normally I average 3 scans of this so that you don't see all this noisiness. But I had to turn off the averaging in this case, because if I waited to average, all of a sudden the clock would change and this whole display would get screwed up. So don't mind the noisiness in here. That's just a measurement artifact. But basically, if you just look at it, you see also very high distortion spikes on one channel. I don't know if you can see the blue in here. It's much worse than the other one. So the second harmonic is much worse. And you can see that reflected in this SINAD rating. One is 89 dB, the other one's 81 dB. So 8 dB difference within the 2 channels. So that's a lot of mismatch to have. 1 or 2 dB difference, I see that in many DACs. But 8 dB means just a tremendous lack of precision in design of that circuit. And, when you go discrete, you wind up losing that kind of precision, and you better have feedback or other mechanisms to compensate for that, or some kind of, hand selecting components, but clearly that wasn't done. The DAC produces 5.7 volts instead of a nominal 4 volts, which is fine. And I lowered the input to it. There's no volume control, by the way. DAC, this giant that's big, it should have remote control on the volume. Doesn't have it. So I dialed in the input in digital domain 2 dB to get it close to 4 volts on this thing. And so running with this number, as far as this distortion and noise combined at 1 kilohertz, I averaged the 2 channels when they're different, and the rating winds up way into the poor category. I don't tell you to try to focus on exact numbers, but I've got broadly 4 buckets that a DAC can fall into as far as sum of noise and distortion. And, when anything's in the red, just means there was no attention to detail. It's like going to a restaurant and you literally can see your plates are dirty and food stuck to them from previous dish that you served to somebody else. That's what this red category is. Maybe you won't get sick, and in this case, maybe you won't hear the artifacts. But I sure as heck don't want to spend any money for a DAC that lands in here. If you want to see it better, it still doesn't show that well in the review, but you can click on this thing on the website and see it clearly, and you can see all of his neighbors in here. And it's not in good company. There is an Apple dongle here that's about 100 SINAD, and this one's at 81, 80, 83, or whatever the averages out. Interestingly enough, when I changed the digital input from USB to coax or Toslink, the results are very different. First, that clocking issue disappears. So that means it's not an instrumentation problem with me or a device being broken per se. It's just that interface with that external USB input is done poorly. So when you use coax, for example, you can see that the frequency is stable at 1 kilohertz. But then we get new problems. Look at all this junk in here around our main tone. Our main tone is this one spike, by the way. Everything else is unwanted. None of this should be there. An ideal device would have this one spike, and this noise floor would be off the charts. Even the best device won't have a noise floor that falls off the chart. It'll be down here. But they wouldn't have all this garbage in here. We have a whole bunch of stuff. There's a bunch of things from multiples of 100. I don't know if that's power supply noise, 120 hertz, and multiples. It could be ORs, 100 hertz. But regardless, there's also some crazy amount of spurious tones in here that just give this thing what I call a skirt. And none of that should be there. Should be a clean, pure spike in here. And then we have harmonics in here, the second and third harmonic, and then fourth and fifth and sixth and seventh, and goes on this thing. It doesn't impact the SINAD score that much. It changes a hair because the distortion is so loud that it dominates the score, but this other junk is also there. And that was with coax input. With Toslink input, it changes again. It's still dirty, but it changes again. So what this says is that the activity inside the device, depending on what input you light up, there's different profile of noise and garbage bleeding onto the DAC channels. That's the first thing you want to do when you design what is called a mixed signal device. We have digital circuits in the DAC, and we have analog circuits, and they're very, very sensitive. And you want to isolate those two things. And they seem to have done it on paper with that middle card being all digital and the two sides being the analog thing. But physical separation is only part of your problem. There are connections that go from digital to analog section, and they're bleeding noise into there. And something that you can't see in here, and sorry this text is obscure, but it says that the noise floor was moving. When I was watching this display in real time, I would actually see the noise floor rising and going up and down. So even getting modulated up and down on this thing. So some other low frequency changes in operation of the device was bleeding into the DAC, both channels of the DAC. One channel I think was worse, the one in red. And it was just climbing up and down, swinging up and down on its own. So all of this basically, again, going back to that dish analogy, it just means you're finding all kinds of, they bring you bread in the restaurant, and bread is stale and mildewy, and your glass of water comes in, and the glass is dirty. It's like everywhere you look on this, graph just shows you that just noise and poor attention to proper execution. Sure, you want to use those, older DACs, go ahead and do them, but at least produce clean, nice, best performance those Dac chips can produce. Don't just bleed a whole bunch of noise and stuff in there where your job as an implementer is to not screw up the performance of that Dac chip. If we take its just signal-noise ratio, all these noise problems come back to haunt it here too. Signal noise ratio is 17 bits. So you might say, well, it's a little bit better than CD at 16 bits. But yeah, you're paying $2,500 for something that barely can reproduce the noise floor of a 40-year-old CD standard. State-of-the-art products go to 22 bits, and this number would be 125, 126. So what this says also is that if you play at 100 dB peaks, your noise floor would be audible at your, from your speaker, because of the 100 dB down is where this thing generates noise, and that's above threshold of hearing. So even if you want to make an argument, oh, maybe I won't hear those. Well, if you turn it loud enough, you will hear noise floor. And by the way, the noise is additive, so this is just your DAC. And then if you hook it up to an amplifier, headphone amp, or power amp and everything, all those noise floors keep cascading and adding up. So your source, you want it to be very clean and very transparent, and clearly this is not transparent, and this is all at the feet of the designer as far as implementing things. So far, I've only shown you the measurements for the balanced output, the XLR output. It also has a set of RCA outputs. First, I measured with balance. This is intermodulation test, so it has a 60 Hertz tone and a 7 kilohertz tone in a 4:1 ratio. So this test, intermodulation test, simultaneously measures the performance of the DAC in both low frequency and high frequency, and then you see it as a combined single IMD number that is then plotted depending on the input level. So the input levels start very low and gradually go all the way up to the max. And I have two references for you. In blue is a state-of-the-art, a very good DAC that came out 2 years ago, topping the X3 Pro. And that's a $200, $250 DAC and headphone combo. It's down here. And then I have one in orange, which is a Razer, the phone company, headphone dongle, which is a $9 little dongle you connect and lets you listen to your headphones on your phone. And the performance of this Audio-gd Master 7 is the same as that dongle. As you can see, in one channel, it barely is better than the other one with balanced output. So as it is, it's quite embarrassing that a $9 dongle has less noise and distortion, or similar noise and distortion than that. But amazing thing happens the moment you hook up an RCA output. Look at what happens to distortion and noise. It shoots way the heck up around minus 30 dB. And then it finishes around minus 40. I mean, that's just 40 dB worse than balanced output. I mean, it just must be a hack of how they implemented unbalanced output without a proper merging circuit converting differential to undifferential. It's just not excusable. I mean, any device that I've tested recently, or even budget desktop products, when they have both connectors, they do a half-decent job of at least getting these two to be very close. Usually 2 or 3 dB difference, not 40 dB difference in performance. So the RCA output in this thing is just truly junk and hard. Suggest if you have this device, this DAC, just use balanced output, XLR output on this thing. So I went ahead and, by the way, plotted the spectrum just to see what it looks like. So this is our dashboard again. Now 2 volts unbalances half the output. And look at this. Now we have almost 0.3% distortion. So forget about having lots of zeros in here. We can't even get 1 zero squeezed in here. And look at the second harmonic. It shoots way the heck up here. And so do the other harmonics in here. So you get this whole spray of harmonics, and we still have all of our noise in here. So very, very embarrassing, just totally unacceptable performance. I was surprised actually in jitter test for USB was actually quite good. So that Amanero module they use must have a good clocking circuit in there that actually produces pretty low noise and distortion, relatively speaking. Again, their desktop DACs, they're much better than this. But for this device, in blue is the USB, it was clean. But I switched to Toslink and coax, all of a sudden the noise floor jumps. These two are Toslink and coax. And as you can see, they have different spurious patterns that don't match each other. So on this thing, so it just another black eye for this DAC. An ideal DAC wouldn't care what digital input you use, right? Bits are bits, digital is digital. Well, bits are not bits for this DAC. Depending on which input you use, different parts of the circuit light up and they create different level of noise and interference. And so you're kind of stuck. If you use USB, you have that clocking error that's going to cause glitches every 1.5 seconds. If you use coax and Toslink inputs, then you have high noise floors and much more jitter. So really poor. It did better in this multi-tone test. This multi-tone test has 32 tones simultaneously put in one waveform. And the level, though, is lower, even though it says 0 in here, is lower than the 1 kHz tone I had in there. So it doesn't generate as much distortion. So it allows the device to perform better now as far as distortion-free range is 15 to 17 kHz. And you can see this rise in distortion. So the higher the frequency, the worse it gets. And that's typical, though, again, this is unacceptable level for anything that's half decent as far as DAC is concerned. Since the output is more than 4 volts, I often run a sweep and show you whether there are more optimal positions than the one that I measured. I measured at 4.3 volts. So I went ahead and sweep the input level and step it up gradually, and then we measure the output level and show it over here. And then we also show the SINAD, which is THT plus noise. And usually the graph sort of climbs like this, and then some devices saturate and then it comes down. This one is sort of does that a little bit, but then all of a sudden performance drops halfway in the middle. Like it doesn't like to output 1.5 volt output. Then it gets better again. Clearly, this is just design error. I've never seen anything like this. This makes no sense. It should be noise at the bottom, and that dominates and causes the curve to go up, and then it saturates at some point and comes down. So we see the saturation coming down, and ideal output is around 4 volts. So what I measured is more or less this, what it best it can do. But the worst it can do is actually around 1.5 volts. So to the extent that the input digital samples get lower in amplitude, all of a sudden it has higher distortion and noise than if they're maximum or at lower levels. So you have to shake your head. I don't know what else you do. And that shaking of the heads continues in that I have this linearity test. Ideal linearity would be that we get a flat line in here. This is the smallest signal that could feed the DAC, and this is the loudest signal that could feed the DAC. It does okay here, but as it gets lower, it has a simple amount of error. It steps down and stays there and sort of gradually gets worse, then it steps down again, and then it picks up some noise. This kind of wiggliness is not great, but we're going to get that at these very low levels. But this kind of steppiness just means precision error in output stage and a buffer stage that it has post the DAC. It basically has an offset and a few microvolts and causes this error to show up, whereas half a dB of error in amplitude by the time you get down to minus 95 dB. So signal design error. Typical of these DACs, they go for what is fashionable, and it's fashionable these days to basically have no filtering. Nyquist's theorem says a digital DAC, a digital system of analog to digital and digital to analog conversion can be perfectly accurate as long as you chop off all the high frequencies above half the sample rate when you digitize it, and then you do the same again when you convert the digital back to analog. So whoever created your music probably has done that, probably filtered everything. But at playback time, this DAC chooses to not do the reverse. It instead has this very slow filter where it just, this is where the line I've drawn is where it should go down to nothing. So it should be like this, flat, and then it should go down. And now that's an ideal DAC. Non-ideal DACs sort of go a little bit past it. But this thing does not even want to attenuate even when you go way past it. So it's basically allowing ultrasonic junk and noise to come out of the DAC. That with a high bandwidth amplifier, it'll also get amplified and it'll get sent to a tweeter. Most speakers and tweeters don't go that high, so as a practical matter, it probably doesn't do much. But there's just no reason for it. It's all folklore that this kind of DAC, this kind of filter does better. There's a jumper in there. You can change things, but I could not understand their English, and I'm very good at reading, poor English that's translated from Chinese or Japanese. But I could not make sense out of what they were saying the jumpers did, so I did not attempt to change it. The owner had not changed it, and this is exactly how the box ships. So to the extent people don't muck with it, this is the filter response. Now, our final test I run gets impacted by that, and this is our, when I show you the dashboard tested 1 kilohertz, one frequency only. Now, a well-designed box will not care about what frequency you throw at it, but not all devices are well-designed, and even well-designed ones may have more distortion at high frequencies or low frequencies or anywhere else. So to detect that, I run a sweep now. I tell the analyzer, look, change the frequency from 20 hertz to 20 kilohertz, the audible band, and at every step, pause, measure THT plus N, which is, our SINAD, basically. And it's expressed as a percentage on the left and expressed as a dB on the right. And go ahead and plot that. So if I just run that test, actually, let me step back. At every point, we want to measure the harmonic distortion. That means multiples of our test tones. So we're at 20 kilohertz. The second harmonic would be 40 kilohertz. Third harmonic would be 60 kilohertz, and on. So for this test to produce correct result, the bandwidth needs to be a lot higher than 20 kilohertz to be able to capture all of that in the analyzer and see the harmonic distortion. So to do that, I have a bandwidth of 90 kilohertz in here. So I can go 4 times the 20 kilohertz in here and capture up to fourth harmonic. The dashboard only runs at 22 kilohertz. So the dashboard is good enough for 1 kilohertz tone, but doesn't include all this noise above the audible band. This one does. So when we do that, when I run this test at 20 hertz, the distortion is already hugely high. This dash line is a $99 board that was a bargain a few years ago, and today that's average performance, and it's down here. And look at how much worse the distortion is in this Audio-gd. And then as the frequencies go up, it gets worse and worse and worse. It actually goes off the chart. It'll actually keep climbing, going crazy land. And up here it's already at 1%, and it'll keep going. And this gets caused because of this filter. This filter is not getting rid of the extra mirrors that are generated of our tone, and they get added in and get expressed as noise and distortion, and so they inflate this number. To remove the effect of this slow filter, I can also run the same test at 192 kilohertz sampling. I won't talk about why that's the case, but when I run it at 192, it basically assumes we now have a perfect filter. Even when I do that, look at the response. First, the 2 channels don't match. One is a lot more distorted than the other one. But look at how much worse the distortion is. We're now to a SINAD of only 65. Remember, I showed you about 80 to 90 dB at 1 kilohertz. But at 20 kilohertz, distortion has shot way up by almost 20 dB worse distortion. And we're now at 0.05% distortion. So very, very poor. And again, the 2 channels don't match. And way worse than even bargain DACs that you can buy today. By the way, this is one reason why you want extremely good SINAD scores at 1 kilohertz in a dashboard. Because if an engineer's done a phenomenal job in here at 1 kilohertz, then chances are, even if there is a rise, it won't climb this high. And you can see that indeed in this bargain DAC in here. At 1 kilohertz is down here, a SINAD of about a 105. So yes, it also climbs up, but it climbs from such a good floor that it only climbs up to minus 85, so it's still extremely good. This one starts at such a poor SINAD of 80 dB here at 1 kilohertz, and then it goes up similar amount, but now it's in really, really poor category of DAC performance. So where are we? Same place we were. Company has shown another measurement on their website that you can't make heads and tails, but it's an audio precision measurement. So clearly the company cares or promotes measurements. Otherwise, why would they stick an audio precision output plot in there? But it definitely is not of this device. It may be a prototype, maybe something else, maybe made up. I don't know. What I do know is that nothing in there I can generate. And by the way, what they have is not great either, but what I'm measuring is far worse than that. So what do we have in here? We have a case of a designer either personally believing or chasing audiophile hype and myths that you want to use these older chips that the companies who designed them are considering them obsolete and discontinued, but somehow audiophiles know more than the chip company and they think they sound better and perform better. Fine. Go ahead and execute and build a DAC that is as good as that chip can deliver. And here they got 4 of them together. That means it should be a lot better, should have much better dynamic range. No, what's been put around those DAC chips is just horrific, and the design is simply not verified. All you got to do when you design a product like this, make a suite of measurements like this. They have an audio precision analyzer. Run these measurements and look at these things. I mean, there's no way any of this is planned. You can't tell me that a designer thought all this grunginess that they added to the noise floor, it's goodness for you. Every audiophile gushes about, blacker backgrounds and deeper into the noise floor. While this thing is a noise factory, it's also a distortion factory, but not any kind of tube distortion or anything you can say is euphonic. Most people will not, I'll guarantee you audiophiles can't hear these distortions, because if they did, they wouldn't buy this product. They would return it right away. So it's not good distortion either. It's just bad design, and they get away with it because of the aura they have and the branding and the reputation, and the fact that, as audiophiles or as people, we're very forgiving of nonlinearity and distortions like this. So we get to not hear it, and instead we let ourselves get biased by the reputation and the size and the weight of the box and what somebody says on the internet, and go and write them a $2,500 check when you could buy a $100 DAC that runs circles around it, and maybe you won't hear the improvement, but you sure as heck your bank account would be much richer because you have $2,400 you can put towards music or do something else for your hobby. So absolutely, please, please avoid buying any product that I haven't measured. I don't want to say everything they build is bad, because I haven't tested everything they built. I can tell you that everything I've tested all follows in the same path of them following myths and building products with no feedback and all these things that audiophiles think is better. But the proof of the pudding is that when you measure it, you can see there's no betterness in there. You can see carelessness in design. And by the way, this company is impossible to deal with per se, in that you want to buy this DAC, you have to PayPal the money in advance to the company, and then they go ahead and send you a product. Now, I haven't seen anybody get ripped off that way, but should they take your money and then close the doors next day, how are you going to get your money back? And it just doesn't make sense. If you're going to sell $1,000, multi-$1,000 products, pay somebody $5 to set up an e-commerce site for you. And heaven forbid if you have to get warranty service on this. If I have a $200 DAC that goes bad, I don't want to send it to China. I'll go get another one. $2,500 DAC, you're going to want it repaired. And to pack and ship a 40-pound package to go back to China and have it come back to you in one piece, and how long it takes. gosh, you gotta have really, really, really good reason to go buy this DAC. And I can't give you any reason to buy this DAC. So anyway, I don't want to keep ranting on this. Hopefully you found it useful in covering yet another type of digital to analog converter. Okay, see you in a future video. Bye-bye.